Hello, student. Uh, this session is going to be hands-on with R. So what I'm going to do, I'm going to use the Colab notebook to introduce you to R so that we can talk about how to implement using R. So I'm using Google Colab notebook because one of the advantage of using Google Colab notebook is you don't have to worry about the installation and all, and you can and it automatically takes care of all the versions and stuff like that. So if you can see this my desktop, then you can see first thing you have to do is in Google Colab default is Python. So first you have to click on the runtime and change runtime type. I have already chosen Python R, so that's why it is R. But typically you will see it is Python 3 is there. So what you have to do, you have to choose R and then save. So if you remember, we have discussed about the bond prices, and in this is the pseudo code that we have discussed, that how to calculate bond prices, and this is the R code I have generated here. So you have to write as a function, and you have to provide three argument: cash flow, times, and the interest rate, or the discount rate, often time we call it. And then first you have to calculate the discount factor, and then if you just these are the two, cash flow is a vector and discount factors will become a vector, and then if you just sum them up, that is total, and you return total. The example that we will choose, that suppose I have a cash flow which is first month, it is first installment, it is 100, second installment it is 100, and the last installment is 1100, and R is 0.05. So if I run this first time, it generally take a little bit of time to connect the Google Colab server. And you can see that the bond price here turns out to be 1136.16. Now, if I reduce the R value from 0.05, remember that it will supposed to 02. So previously it was 1136. Now if I run it again, now it is 1230. So as I reduce the interest rate, the bond price increases. If I increase it to 0.07, the bond price will drop to 1078. This is always the case. If the interest rate increases, the bond price decreases, and if the interest rate decreases, the bond price increases. So you always keep that in your mind, and they have an inverse relationship, and the inverse relationship is very nonlinear in its nature. Here is another example where we have over five time points over say 2.5 years. So first 6 month 25 rupees, then first year, end of first year 25 rupees, third year 25, 18 months, and the 24 months. And then at the end, it returns 1025 rupees, and the interest rate is 0.08. So the bond price will be 1023. But if I increase it to say 0.05, then you will see bond price drops to 891. But if I drop the interest rate to 0.01, then the bond price increases to 0.072. But if you carefully notice that you can handwrite in your notebook that what are the interest rate and what is how the price is going up and down. This up and down is highly nonlinear in their nature, so you have to be careful. Now we will talk about that. Suppose you have 100 rupees at a different kind of conversion. That annual conversion will, if you have a 8% nominal rate, at the end of the year you will get 108 rupees. At semi-annual conversion rate, you will get 108 rupees 16 paisa. At a monthly rate, you will get 108 rupees 30 paisa. If the conversion rate is daily compounding, then it is 108 rupees 33 paisa, and if it is a continuous compounding, then you will get 108 rupees 33 paisa. So what I have done here, I have taken the basic principle is 100 rupees, nominal rate is say 8%, 0.08, and the time of the year is 1 year. Okay. Then what I have done, calculated the annual conversion rate is principal times 1 plus nominal rate to the power time of the year. In the semi-annual compounding, I have two compounding. Semi-annual rate is nominal rate divided by the semi-annual rate. And then principal is times 1 plus semi-annual rate divided to the power semi-annual compounding times time of the year. That is, you have to be careful. Then monthly compounding will have 12 compounding. So the nominal rate, you have to divide that by the monthly compounding. How many compounding you are doing, that will give you the monthly rate, right? And then principal times that 1 plus monthly rate to the power monthly compounding times time years. Time years is here 1. Similarly, daily compounding, here you can compute the daily future value. And then finally, if you create, I have here created a data frame to present the above result. So if you see that the same thing I just developed for annual compounding, it is 108 rupees, but the continuous compounding 108 rupees 33 paisa. Next, we will move on to algorithmic compounding of e to the power x via Taylor series. So if you remember, we discussed this pseudo code, that exponential of approximating exponential of x e to the raise x with a some tolerance level. So you take the total value, total is 1, then term is 1, n is 1. And when the absolute value of term is more than tolerance, you compute the term times x by n, and total is equal to total plus term by n. Calculate the n equal to n plus 1, and you keep doing it until you converge. This is exactly what we have written the function here, x and tolerance, x to the power, then total term and n. And then while absolute value of term is greater than tolerance, this is exactly the way we have written. So it is almost like a pseudo code the way we have written. And then what we have done, so this we have called the exponential function. The output should be e to the power 2 we have calculated, and the approximate value should be 7.389056, and exp is a built-in function in R. Okay, we compare our function, the result output from our function with the built-in function in R. Okay, so let us do that. So you can see that our function, our result gives 7.39056, and the built-in function also give exactly same value. Okay. Now what I'm going to do, I'm going to use the the same value, but I'm going to approximate the how much time our function is taking and how much time uh, built-in function of R is taking. We are going to clock the time, and that is it is very important uh, in computational finance. And let us run that. So our function, the output exactly matches. It took 1216.65 microsecond, and built-in function exp, it took the exact same, result matches exactly same, and it took a little less time, 1147.032 microseconds. And if we run it few more times, so here also it took 901 seconds, 889 microseconds. Again, if you run it few more times, you will see most of the time our result, we are having the same result, but our function is slightly slower than built-in function in R. Uh, One of the reason why we are interested about time, especially runtime. Now imagine you are using compounded, this continuous compounding approximation to price a bond, and you are doing it for a portfolio which may contain, you have in your market, you have 10,000 possible prices, and out of 10 bonds, and out of 10,000 bonds, you want to choose only 20 bonds. But for 10,000 bonds, you have to calculate the prices. So for each prices, you have to compute these e to the power, the value. And for each prices, if you take like some microseconds delay, it may add up to few minutes to maybe 1 hour delay, depending on how many such computations you are doing. Okay, it depends, completely depends on how much compute power you have and all those things. So in a world of computational finance, you have to be careful about the runtime complexity and how much time it is taking. Okay, so this was the last thing we checked it, that 0.1 plus 0.2 is logically not equal to 0.3. It returns false. We know it is same, but and one reason is 0.3 is it 0.333? Is it one third? How do you define that? So those are the issues that floating point things does not match. So you have to be either greater than equal to or less than equal to is much more easier thing. So you have to be a bit careful about all these things. I'll stop here, and we will see you in the next week.